Hi, my name is Antje Bart. I work as a developer advocate for AI and machine learning at AWS. In this session, I'm showing you how to build consistent and portable machine learning environments with containers. First, I'm going to introduce you to our use case. We're going to build a BERT-based NLP classifier model. Then I'm briefly explaining why we're talking about machine learning with containers. And I'm showing you how to use containers with Amazon Elastic Kubernetes Service, EKS, and how to use ML containers with Amazon Sagemaker. And of course, we'll see a demo. So let's start with our use case. Meet Sarah. Sarah is a data scientist. She recently started at Amazon. She joined the customer reviews team, and her first project is to build a BERT-based NLP model to classify customer reviews coming in from the Amazon.com marketplace. So for example, I simply love this product, should be classified as a 5-star rating. So let's have a look at Sarah's workflow. Everything starts with high-quality data. And luckily, we do have a public dataset available, the Amazon Customer Reviews dataset, which consists of over 150 million reviews from the Amazon.com marketplace. So let's use that one. Then, Sarah also heard that there are pre-trained BERT models available. That means she doesn't have to train the model from scratch. She can rather use one of the pre-trained ones and really just fine-tune it to this specific data set. So I think that's a good choice. All right, and Sarah starts prototyping the model code in her Jupyter environment. After a while, she really gets okay results. So now she needs to move the code to a training environment that has more resources so that she can run more sophisticated, more complex training jobs on more data. All right, so she's moving the code over to the other environment, and shoot, something isn't working anymore. The code doesn't run as expected. And I would assume many of you have been in a similar situation, including myself. When you try to port code that you developed on one environment to another environment. And this is the reason we're talking about machine learning with containers. Containers really bring the same advantage to your machine learning projects as they do to application development. So think of all the projects you're working on. You might be developing one project with TensorFlow and another one in PyTorch or MXNet. And probably all of those will have different dependencies or at least different library versions. By packaging up all your training code, your dependencies, and your configurations, you will get environments that are now lightweight, portable, scalable, and consistent. So once you've packaged everything as a container, you can then simply push it to a container registry, such as the Amazon Elastic Container Registry, ECR, and then in another environment, do a pull and run the container there. And the good news is that you don't have to develop the Docker images yourself. You can leverage the AWS deep learning containers. Those are pre-packaged Docker container images which are fully configured and validated. They support many of the popular frameworks such as TensorFlow, PyTorch, or MXNet. They support also single and multi-node training and inference. And you can run them on Amazon SageMaker, Amazon EKS, ECS, or EC2. All right, so Sarah is really excited about trying out those containerized environments. So there's a couple of options she could look at. First of all, she could use her own container, or she could leverage the AWS pre-built deep learning containers. For the execution environment, she could decide to run them on ECS or on EKS, or she could leverage a fully managed service such as Amazon SageMaker to run her model training with the containers in that environment. So let's have a closer look at those two options. Let's start with how to use containers with Amazon EKS. Let's assume she wants to build her own container. How does this now look? So first of all, running containers on EKS requires you to have an EKS cluster. Then you start developing your code. And this could be your model training code, your model inference code, etc. You also now need to build your custom container. So you're going to develop a Docker file which contains all of the code and library dependencies. Then you build the container and you push it to the container registry. Once you've done that, you need to create a YAML definition so you can execute the job on the Kubernetes cluster. All right, maybe that's a little bit too much work. So what you can also do is leverage an AWS provided container. So you can skip the step of building the Docker container yourself. It also starts with an EKS cluster. But now the difference is that you can focus on developing your code, your model training code, your model inference code. And what you then do is in the YAML definition, you point to the existing Docker container image, for example, the AWS deep learning containers. And then you're applying that YAML file on EKS, and it will execute the training job. Note that in this environment, you will still have to take care of all of the Kubernetes specifics, especially if you want to distribute your model training job. And if you now wonder how a training.yaml looks like, here's an example. So you can see here that in the container definition in my YAML file, I'm pointing to my model training code, the train.py file. And I'm also passing in hyperparameters here as command line arguments. Then I'm pointing to this Docker image, and here in this case, I'm using a pre-built container image. And I'm also mounting an Amazon FSx file system. And I'm using this high-performance file system as a distributed file system and a persistent volume client in my EKS cluster, so I can have access to my code files and the training data from the container environment. In my training code, I can then use those hyperparameters. So here you can see how I actually use the learning rate and the epsilon in my training code, which I pass in here in the YAML definition as hyperparameters. And I can also leverage the distributed file system to write data to and read data from. So for example, you can read the training data and you can write your trained models to that file system. All right, so let's have a look at the second option, how you can use containers with Amazon SageMaker. Amazon SageMaker is a fully managed service which helps you to build, train, and deploy your machine learning models quickly. And it comes with different levels of customizations. If you don't want to write any code at all, you could use the built-in algorithms, which come already with a container and all required code. They support a lot of the popular machine learning use cases, as you can see. But again, Sarah wants to write her own custom machine learning model code. So there's another option, which is called script mode. And in here, you can leverage the pre-built framework containers, which are based on the AWS deep learning containers. The second option is you can also bring your custom container if you need that flexibility. All right, so let's have a look how that works. So now Sarah sits on her laptop and she uses the Sagemaker Python Sdk to interact with SageMaker. And you can see here in this code snippet in the upper left, down left, that she's creating a TensorFlow estimator. And she's pointing that estimator to her training script, which is the training.py. She specifies the source directory, and Sagemaker basically combines your code files and uploads them to S3, where Sagemaker and their container can have access. She also specifies which instance and instance types to run it on. And this is really nice because now you don't have to care about the infrastructure. Sagemaker will take care. Again, in comparison to EKS, which is a predefined cluster, Amazon SageMaker manages all the infrastructure for you. So here you can dynamically change, for example, from a CPU instance to a GPU-based instance, or do distributed training by just increasing the instance count from 1 to maybe 5. All right, so again, the steps. Sarah starts writing her model code. And then in this TensorFlow estimator definition, she specifies the framework version. And this will basically pull in the right framework container to then copy your code files and execute it on the instance you specified. And the results will be written back to S3. All right. How does it look if you're doing a custom container? In this case, again, you have to involve Docker steps. So you develop your code, you develop the Docker file, and you could, for example, use a service such as AWS Code Build to build the Docker file and then push it to the registry. And in the estimator definition, you can see now that I'm specifying the exact image to use. And SageMaker will pull that image, again, wrap your code from that image, everything, and deploys it on the instance, executes it, and will store all of the outputs, the model artifacts, in an S3 bucket. All right, so let's see this in action. So here I'm in an AWS environment. And to start building our model, we first need to prepare the data. Again, I'm using the Amazon Customer Reviews dataset, which contains a lot of information, as you can see here, from marketplace, customer IDs, review IDs, product IDs, etc. We're specifically interested in the star rating, which is the review rating, the 1 to 5 stars, and also in the review body, which is the actual text of the review. Now, the feature transformation that we need to do is as follows. We're taking the star rating and the raw review text, and to create this NLP model, we need to convert the raw text into word embeddings that the model expects as input. In this case, Bird expects specific inputs. So let's see how we can do this. So first of all, I'm pulling in my frameworks, TensorFlow, transformers, and I'm also pulling down a tokenizer. And by the way, this transformer library is an open source library from Hugging Face. So this is the pre-trained model. I'm specifying my data and value columns, and I'm creating some helper code to create my input features. I'm also specifying a single input, the text and the label. I'm converting the inputs, so this is the important step where I tokenize the raw text. And I'm encoding, meaning I'm creating those word embeddings for the NLP model. And then I'm returning those features. Another step we're doing here is also transforming the inputs into TF record files, which is optimized for TensorFlow training. All right, and if you wonder what those word embeddings look like and the input features, input IDs is the ID from the pre-trained Bird vocabulary that represents a token. The input mask specifies which tokens Bird should pay attention to. And the segment IDs are more useful if you're doing question answering, so in this case it's 0. And the label ID then matches to our star rating. All right, so let's see how this looks. So I'm creating here some sample reviews with a star rating and some sample text. I'm wrapping that in a pandas data frame. And then I'm applying those input transformations. And I'm converting it to TF record. So here you can see how the transform data looks. So here we have our tokens. We do have the input IDs. the input mask, which really shows which tokens to pay attention to if we need to do padding. And then the label ID here, which is representative of the star rating class ID. You can also visualize the T of records. So here you can see how that looks. All right, so let's assume Sarah has prepared all her training data, and we can now start developing our model training code. So first of all, we're doing this in the notebook. And just as a quick recap, we're using a pre-trained BERT model from the Hugging Face open source library. And we do some feature engineering, preparing our training data, convert it into the BERT embeddings. And then in the model training step, we're really just fine-tuning it to our specific data. All right, again, let's start in our notebook here by pulling in the required libraries. And I'm also pointing to our training data. And as you can see here, I do have those T of record files locally available here in this notebook environment. I'm also specifying the hyperparameters. And you want to make sure if you're running this in the notebook that you're choosing low value. So I'm just going to do one epic and just very low batch sizes. This is really just to prototype my initial training code. I'm pulling in here the needed libraries. So from this transformer library, I'm using the distill BERT. This is the type of BERT model I'm using. Specifying the star rating classes from 1 to 5. Selecting the data and the label from the records. Some helper code to help me read the T of records as input files. Decoding the records from T of record. And then I start developing the main model training code here. So I'm reading in all of my hyperparameters, making sure I do have them available. You can also specify where to store the trained model at the end. So I'm defining a path here. You can also start developing some distribution strategies. And then I'm basically starting with pulling down the pre-trained tokenizer, the configuration, and the pre-trained model. I'm specifying my optimizer. I'm defining the loss and the metric. I'm compiling my model. And let's actually print the model summary as well. I'm specifying the validation steps. And I'm also doing some testing of the model. And let's actually also print the test summary so we get the test accuracy. And then I'm saving my model in two formats, one specific to Hugging Face and one really being the standard vanilla TensorFlow format. We can also run some sample predictions. So let's actually log the trained model and give it some sample reviews. So here I'm using the text classification pipeline, again from the Hugging Face library, and passing in some sample reviews. All right, so let's run this code. And you can see here that the training code is now being executed in my notebook environment. It's showing all the environment variables, it's reading in my hyperparameters, and it starts the training. So here you can see it's reading in my training data. We're printing the model summary. So here you can see how the model looks. And also note that we're only training a subset of the parameters. This is because I've frozen the BERT base model. So we're just training, fine-tuning this classifier on top. We're running also some validation. And then we're also doing the final test. And let's actually see how those results look. And here you can see that the test accuracy is around 25%. So it's not yet the best, but again, this is really very small data, really to make sure that our model training code is working. And the sample predictions here you can see coming in with 5 and around the same probability score accuracy of 21%. So let's now take this code and execute it on EKS. So in preparation for this, what I've done is spinning up an EKS cluster in my account. So here you can see the EKS cluster being active. And what I've also done is I've set up an FSX for Lustre file system, which I'm going to use as my distributed file system in EKS. So I do have a persistent volume claim available where I can retrieve files and then write them to. So if I flip over here to my FSX, you can see the file system. And you can also integrate the FSX file system to an S3 bucket. And this is exactly where I stored my files. So you can see here the train.py and also all of the training data. And we're going to use this to give the container access to this environment. Quick summary, here you can see how the structure is in my S3 bucket with the code and input directories. You can do a quick ls command, a show command on that bucket, and you can see the individual files. All right, so the next step is to take our model training code that we developed in the notebook environment and now take it into a train.py file. And this code should look familiar to you. It's pretty much the exact same code that I developed in my notebook. I just used it now to create this train.py file that we can use with EKS. And the next step is to create a YAML definition. So here you can see the train.yaml. We're creating a pod. Let's call it the bird model training. I'm specifying my FSX mount. And in the container definition, you can see here, call it bird. And it's pointing to my train.py in the optml folder. And optml is basically the mount path where I mounted the FSX mount in the container. I'm specifying my hyperparameters again. And let's actually use a little bit higher go up epic 3, etc. And I'm pointing to the container image. All right, and next step is really to get ready to apply this to our Kubernetes cluster. So you can do a quick kubectl get nodes, and you can see that we do have 4 nodes here available in this demo. And then I'm firing up and applying my train.yaml, and this starts the pod on the EKS cluster. You can grab the pod and see it's running. You can describe the pod and see here that it's spinning up, pulling the image, and starting up the container. And then you can use the kubectl logs command to actually look into the pod logs and see here the outputs of our model training. You can see here I'm listing the opt folder to see that it actually has access to our input training data and training code. It reads in all of the hyperparameters, which we passed in the YAML definition. And again, it starts the training now on EKS. You can see the model summary again, the parameters to train, and it runs the validation and it runs the test. And again, it comes around at the same level of test accuracy with 25%. We haven't changed the code really. We bumped up a little bit the data with higher batch sizes, and you can see it's now predicting slightly better, so we get a label of 5 and a label of 1 now for our sample reviews. All right, so the next step is to take our training code and the container and run it on Sagemaker. So the first step here is to pull in the Sagemaker Python Sdk to interact with the service. I'm defining the session, bucket, role, and region. I'm also pointing to the training data, and this is here the S3 location where I just stored my training data before. So I'm using this for the train, validation, and test input channels. You can also specify a distribution strategy, and this optimizes the inputs with Sagemaker. So sharded by a 3 key means it will shard the input files across the different instances. I'm defining the hyperparameters, so let's use the same ones from EKS. And you can also make sure to grab important metrics. So Sagemaker will write all of the logs to CloudWatch, and we can make sure by giving it regex expressions to capture the important metrics such as training loss, training accuracy, validation loss, validation accuracy. And we're using the exact same train.py code. In this case, I'm creating a TensorFlow estimator. And I'm pointing it to my train.py file, which lives here in this code folder, giving it an execution role, specifying the instance count and type. And note that in this case, I'm using a C5 9x large. I could easily define a GPU-based instance as well. We can also leverage capabilities built in SageMaker, such as bot instances. Also, I'm defining the hyperparameters here, and then I can call the fit on the estimator to run my training job. And SageMaker is now taking care of the job execution. So let's have a look. I'm jumping over now to my SageMaker console, and we can see the job has completed, and it has all of the configuration settings. And we also can see that the spot training already gave us 61% savings over the on-demand instance. It points here to the image that SageMaker used by specifying the framework and the version. We can see the input channels for the training data, validation, and test data, which are pointing to our S3 bucket. We can see the metrics, which we captured, and of course, all of the settings for the hyperparameters, which we passed in. And here you can see nicely how SageMaker visualizes the metrics that we captured. We can also have a look directly into the CloudWatch logs. So let's do this. And here you can see all of our training code outputs again. And let's check for the test results. And again, we will have 25% accuracy. We use the exact same parameters from the EKS run. And again, pretty much the same responses here, predictions on our sample reviews with a label of 5 and a label of 1. All right. So as I said, SageMaker will write all of the outputs, especially the trained model tar file, to an S3 bucket. And here you can see the model tar file, and we can simply grab that and then start over and deploy that, for example, into a production environment as well. All right, so this was a very quick demo here that showed you how you can start developing your code in a Jupyter local environment, and how you can leverage container images to then wrap the code and the environment, and for example, run it on EKS, and how you can also run it leveraging a service like Amazon SageMaker. So let's have a look at Sarah's new workflow. We still need to start with training data. We got that covered. We have a really good training data set. Sarah will also continue to use the pre-trained NLP model, as this saves a lot of time in training. She will continue to develop her own custom model code, so she can do whatever she needs to do some print statements, etc. But she really saw the advantage of leveraging the pre-built AWS deep learning containers to have this consistent environment across the different platforms. And she decided to use Amazon SageMaker to run her model training, as she doesn't want to write YAML definitions and take care of a lot of the Kubernetes specifics, especially managing the distribution of training jobs. And she got really excited about the built-in capabilities of Amazon SageMaker, and she will definitely explore the managed spot training further to save her department extra money and up to 90% compared to over on-demand instances. So as a summary, containers let you build lightweight, portable, and consistent ML environments. You can leverage the AWS deep learning containers, which include frameworks optimized by experts to deliver the best performance on CPU and GPUs. You can build self-managed ML platforms with Amazon EKS and compatible ML toolkits, or you can leverage Amazon SageMaker as a fully managed service to build, train, and deploy your models quickly. To get started, here are a couple of links for you. So first of all, resources around the AWS deep learning containers, a link to Amazon SageMaker, and also a link to the demo code in the GitHub repo I'm pointing here, so you can find a lot of more examples, and also to the Data Science on AWS O'Reilly book, which I authored together with a colleague of mine, which will show you all the steps on how to start building data science projects on AWS from data ingest up to the model deployment. And this completes the session. Thanks for watching.